Okay, so let's put things together again. Once again, some of these steps are detailed in the previous parts. Today's lecture and the previous lectures, lecture 6 and so on. Feel free to pause if you want to review what we did in more details. But if we put together everything from the beginning of the chapter on Bessel functions, we have this starting point basically, right? So a heat equation in cylindrical coordinates. Let's put some boundary conditions. Let's put the Dirichlet type of condition, which means the temperature on the exterior of the cylinder is 0. I call it exterior because C denotes the outer radius. Okay, so the domain of rho, the radius is 0 in C. And some initial temperature on the object, or initial condition, which is U of rho 0 equals some function of rho. Remember, we're going to deal with this at the end, after superposition principle. We impose the separation of variables method. We separate the PDE. And at this point, in anticipation for dealing with Bessel functions, let's denote lambda by alpha squared. So the separation constant is going to be minus alpha squared. So make sure you denote it this way so you can avoid carrying over radicals later on. The boundary condition becomes this, which leads to R of C equals 0. So the boundary value problem, which becomes the Sturm-Liouville problem, is going to be a Bessel equation of order 0 with this type of boundary condition. By the way, we're going to have different types of boundary condition later, but for now, let's focus on this one. So the Bessel equation of order 0 with this boundary condition becomes our eigenvalue problem. And then once we solve this one for each eigenvalue and eigenfunction, we're going to go back here and solve the problem in T, which in this case is going to be just an exponential ODE. So in fact, this one, you're better off leaving it in this form because the solution is just an exponential. Okay, so going back to the Sturm-Liouville problem, we established in the previous part that the general solution of it is going to be a linear combination of the following Bessel functions of the of order 0. So the general solution of R is C1 J naught of alpha rho, C2 Y naught of alpha rho. Automatically C2 is 0 because Y naught is discontinuous. So we cannot have that. And C1 must be not equal to 0. And then from R of C equals 0, we concluded that J naught of alpha C is equal to 0. If you were, again, go back to Maple plot, if you were to plot J naught of alpha C as a function of alpha, so alpha is your variable at this point. This is, again, something that people may be confused at this point. Remember, the goal is to figure out what alpha is. What is alpha so that J naught of alpha C equals 0. But if we plot J naught of alpha C with respect to alpha, you will see, of course, that the Bessel function intersects the horizontal axis infinitely many times. So you simply denote the intersection points, those roots, as alpha 1, alpha 2, alpha 3, alpha j, and so on. And you assume these roots are known, because they are basically, just that you can only approximate them, but because you don't have a closed format for what the solution is. But for all practical purposes, consider these solutions as known. So let's write it down again. Alpha 1, alpha 2, alpha j, and so on denote the roots of J naught of alpha C equals 0. So from now on, know that J naught of alpha JC is equal to 0. Okay, so if you plug in any of these roots into J naught of alpha C, you always get 0 because by assumption, you denoted alpha 1, alpha 2, and alpha j to be the roots of this equation. So basically, at this point, what we achieved is that the eigenvalues of this Sturm-Liouville problem are alpha j squared. Okay, so remember our notation that the separation constant is alpha squared. Okay, so then the value of lambda, if you want, is alpha j squared. So the eigenvalues are alpha j squared, and the eigenfunctions, which now you can denote by Rj of rho. Okay, so going all the way back to the solution here, the eigenfunctions are j naught of alpha j rho. Rho is your variable, okay, for r, right? R is a function of rho. And again, this is analogous previously with saying that lambda is n pi over c squared, and eigenfunctions were sine of n pi x over c. You don't have to write this down, by the way, because I don't want you to get confused between Bessel functions and the previous types of Sturm-Liouville problems, but I like you to compare this because this is really the complete analogy between what we had before and what we have now. It's customary to denote by j the index in this case. I mean, I don't know if it's customary, to be honest, because it's still going from 1, 2, 3, and so on, but just to keep in line with the notation in the book. So j takes all the values from 1 to infinity, 1, 2, 3, and so on. And just like n here in the previous cases was 1, 2, 3, and so on. Instead of x, you have rho, that's the variable. Alpha j squared is the eigenfunction. One thing to keep in mind when you go over these problems is to never lose track of what alpha j stands for, because that will depend on the boundary condition, right? In the case of the Dirichlet type of conditions, alpha j denotes the root, obviously, of this equation of j naught of alpha c equals 0. But in case you have different boundary conditions, let's say a derivative, then of course alpha j will denote something else, will denote the roots of some other type of equation. We're going to leave it at that for today's lecture, for this part of the lecture, but keep in mind at this point that there is one more major hurdle before we move on. Remember, it's not enough to find infinitely many solutions. In order to have a hope of, in fact, coming up with a series format for the solution, we need these eigenfunctions to be actually orthogonal. Because otherwise, we cannot produce a series representation. Remember, the only reason this works in the previous case is because sine of n pi x over c were orthogonal, meaning that you could integrate, you could find a series representation in terms of these functions for a typical function given in the initial condition. And so in the next lecture, we're going to show, just to see how the proof looks like, just for fun, so to speak, but we're going to prove that these Bessel functions are actually orthogonal with weight function x, which allows us to come up with the so-called Fourier Bessel functions. So we'll leave it at that for now, and we're going to do that in the next lecture.